Now let us discuss the radiation field from an arbitrary antenna. Suppose that the current source is an arbitrary vector current density J of R prime, confined to a finite source region V0. Then the vector potential is written as shown here. R is the position vector pointing to the observation point, and R prime is the position vector pointing to the source point. Here, R means the distance between the observation point R and the source point R prime. The electric field is expressed in terms of the vector potential by this formula. Our goal is to obtain an approximate expression when the observation point is very far from the antenna. This is the far field approximation. In this case, the observation distance is much larger than the size of the source region. First, we compute the divergence of the vector potential and then its gradient. To do that, we differentiate R with respect to x, y, and z. These derivatives are written as shown here. For convenience, we remove the constant factor mu over 4 pi and define A prime. Then, by differentiating component by component, we obtain the divergence of A prime. Now we focus on the far field. So, the 1 over R term is dominant, and the terms with higher powers of 1 over R are negligible. Therefore, the result can be approximated as shown here. If we differentiate once more and take only the dominant term, we obtain the gradient of the divergence. Next, let us introduce another far field approximation. In the far field, the observation distance R is much larger than the antenna size. So the direction from the source point to the observer, R hat, is almost the same as R hat. Also, 1 over R can be approximated by 1 over R. However, for the exponential factor, we need the first order term in the phase. This is because this exponential function completes one full sinusoidal cycle over a distance of 1 wavelength, and the difference between capital R and lowercase r can be comparable to 1 wavelength, so it must be retained in the exponential term. So R can be approximated to first order as shown here, and exponential of minus jkr is approximated by exponential of minus jk times r minus r hat dot r prime. Substituting these approximations into the electric field, we obtain the far field expression shown here. The important point is that this expression separates into two parts. The factor exponential of minus jkr divided by r contains the dependence on distance. The remaining integral depends only on direction through theta and phi, and on the current distribution inside the antenna. Therefore, we may write the radiation field in the compact form E of r is approximately exponential of minus jkr divided by 4 pi r times a vector function f of theta and phi. This function f of theta and phi represents the directional dependence of the radiation pattern. So the conclusion is the following. For any antenna, the far field always decays as 1 over r and has the common phase factor exponential of minus jkr. What changes from one antenna to another is the angular dependence. That is the function f of theta and phi.